In this example, we develop the model equation for a Cstr process. We'll consider an isothermal Cstr. Now a brief description about the process itself. A feed with the component R is coming in to the Cstr. R reacts to produce some product P. So the reactant R is converted into product P. We're not going into the details about the reaction itself. We'll use only the knowledge which is required for developing the model equation for the purpose of control. We have some more information that the rate of reaction is some function of the concentration of Cr, which is basic understanding of chemical kinetics. Now here a little bit of notation. We'll consider Fi to be in terms of volumetric flow rate. Cr and Cri, we'll consider this to be in terms of moles per unit volume. So whenever a reaction will be considered, we'll consider this concentration to be in terms of moles per unit volume. Now for this case, we'll consider an isothermal reactor, meaning that this K remains constant. Okay, that simplifies the model equation for this case. Now we'll follow the step-by-step procedure. So in step 1, defining the modeling objective. Now we'll try to find out how the Cr changes with change in Fi and Cri. We can see that both of the variables can be related to Cr using the same equation. However, one variable may be the input and another variable may be considered as the disturbance. So both with the change of input and disturbance, the output will change and those will be related by the same equation. So step 1 is we consider output to be Cr and the input can be Fi and the disturbance can be Cri. Now with this, we'll try to establish the link between the variables. Now from process knowledge, you can think about if there is a change in Fi, that will have an effect in Fo, outlet flow. So that equation, one equation we will have. Also if there is a change in Fi, that will affect Cr. However, Cr may also have an effect on the Cr itself, meaning that the rate of reaction depends on the concentration of R, and in that way, with the increase and decrease in Cr, rate of reaction will increase or decrease, and that will also affect the variable itself. So there is a link between Cr itself. Now with this, we'll need some process information which are again given here, that a reaction taking place. So these are more or less the information required for step 2. There will be other information required for detailed modeling, for example, the volume, volumetric flow rate, and so on. So that can be covered for the purpose of detailed modeling. Now we'll move to step 3, which is our main focus. So for step 3, for this case, if we write down the overall mass balance, we have seen for the tank case, we will end up getting Fit equals F naught T, simply because it's a constant hold up. Now we'll move to the component balance, which is more relevant for the case. So for component balance, again, we'll have accumulation equals in minus out plus generation minus consumption. Now here for the accumulation term, we'll have VCR and for the examples involving reaction, we'll assume that this concentration is given in terms of moles per liter. So we need to multiply it by the molecular weight to get the mass. So at the rate of change of this will give the rate of accumulation. Similarly for in, we get the flow rate times the molar concentration and molecular weight minus, similarly for outlet, we'll have F naught Cr Mr. Now I'm just writing this, simply omitting the term as a function of time to make it simple. And we have the rate of consumption for this case, KV Cr to the power the reaction order. Now think about here, we have written it a simple way that R goes to P. In a real reaction scenario, we'll have something like R plus other reactant producing P plus other product, be more than one. So here for this case, the R is the limiting reactant, meaning the rate of reaction depends on R. That's why we are just considering the reactant R here. To remember that if the reaction rate depends on other reactants or product, in that case those will need to be taken into account. Now considering this for the constant volume case, we can write there will be an MR here to convert it into mass. So the MR term cancels from each of those. And we have, for example, for a simplified case of reaction order to be 1, we can write V dCRT over dt. This time we can just replace FO by Fi from this relation. And then if we take this on the other side, we'll have Fi plus KV CRT will be Fi dCRI. Typically, this is written in a way dCRT over dt plus Fi over V plus K times CRT equals so this is one of the typical form. That's the equation is written as. So this is the equation relating this composition of the component R and the inlet flow and also the inlet composition. Now here we considered isothermal reactor. What is the temperature term here? It's here in this term. But we know that K equals some K naught e to the power negative E over RT from our chemical kinetics knowledge, that if T is constant, so for K will be constant. However, later in other examples we see that this K will not remain constant. So when the temperature is a variable, we'll see that this also needs to be considered. Here that will result in a term with a nonlinear appearance of the temperature term there that will need to be linearized. Now again, for this case, we have written it for a simplified case of rate equals 1. And the reaction can be for different orders and that needs to be taken care of. So finally, we get this equation relating the variables for the reactor case with constant holdup. Now let's consider the case with the isothermal reactor with a variable volume, meaning that for this case the outlet is from the bottom and that may be due to the gravitation. Now for this case, if you write down the overall mass balance equation, you'll end up getting dVT over dt equals Fi minus F. Now the component balance equation, again in the simple form we can write accumulation in minus out. Here we don't have any generation term because we're considering in terms of the reactant, so minus consumption. So for the accumulation term we'll write just to indicate the variability of the volume. So volume times the molar concentration times the molecular weight will give you the mass, and rate of change of mass with time will give you the rate of accumulation. So this will write as equals in minus out minus consumption. So in will be given as FICRI times MR minus F naught CR times MR minus KVCR MR. Now MR term gets cancelled for each of the term, and for this case we'll end up getting the left term to be dt. The right hand side will remain the same. Now for the left hand side, now if I just write this to be the left side equals this, and I replace dv by dt with a phi t minus FOT, I can get the left side to be V plus Cr Fi minus Fo. Now if you compare this with the right hand side, what you will get that Cr times Fo term is on both sides, and that will get cancelled. So we'll get the entire equation, this equation as on the left side we'll have V over dt plus the F naught Cr times Cr get cancelled. We'll have the term Fi Cr if we write CRT. On the right hand side we'll have this term, and this term get cancelled, and we'll have this term. So I'll just take this term on the left side to get, on the right hand side we'll have only one term, Fi Cr. Now in a further standardized form, this is written as d Cr plus Fi over V plus K Cr Now you see that the form of the equation remains the same for both the cases where it was constant hold-up and the case where we have variable hold-up. Now the difference between these two will be when you are considering V is no more a constant, so you'll have to simultaneously solve for V and Cr when trying to find a relation between Cr and Fi. If Fi remains constant, V remains constant, meaning that in the cases where you will be trying to find a model between Cri and Cr, you will consider Fi and V to be constant. However, when you're trying to find a model between Cr and Fi, you will have to solve these two equations simultaneously to get Cr. So again, this is the final form of the equation for this case, and this is the same equation we obtained for the constant hold-up scenario.